All right, so let's look at a couple of examples. I want to do one where it's just the straightforward kinematic equations. Where did those go? These ones here. Okay, and I'm going to do another one where we do that kind of utilize these no slip equations, type of idea. So I want to show an example using each of those parts to find various things. Are we good? Are there any questions? Let's take a look. This will be chapter 9. So I got to specify which chapter because we're doing 2 together, but really we're just in 9 at the moment. This will be number 16. So it reads that it's a flywheel. Okay, now a flywheel is generally a disc or a cylinder that they then rotate to hold energy in terms of rotational kinetic energy on the rotating disc or the rotating cylinder. And then you can use that energy to do other things. So they're pretty common in motors with these kinds of rotations. Okay. So a flywheel in a motor is rotating at 500 RPM. This is going to be a common unit. So this will be in revolutions per minute. And what we're going to need to do is convert that into radians per second from revolutions per minute. So it's spinning at 500 RPM when a power failure suddenly occurs. The flywheel has a mass of 40 kilograms and a diameter of 75 centimeters. The power is off for 30 seconds, and during this time, the flywheel slows down uniformly due to friction. So uniformly slowing down says that the angular accelerations will be constant, and we can do kinematics. Okay. Uniformly slows down uniformly due to friction in the axle bearings. During the time the power is off, the flywheel makes 200 complete revolutions. At what rate is the flywheel spinning when the power comes back on? And then how long after the beginning of the power failure would it have taken the flywheel to come to a stop if the power had not come back on? And how many revolutions would the wheel have made during this time? So what we're going to do is we're going to do something very similar to what we always did in chapter 2. We're going to start off with a nice diagram. So we're going to have a flywheel, which again is a rotating disc or cylinder. Okay. Going to rotate through an axis at the center of the flywheel. And what we're going to do is we're going to track a point on the edge of the flywheel. So this will be my initial point. We'll just pick it to be along the, the plus x axis. So then I can claim that my initial angular position is going to be 0. Okay. And it's rotating very, very quickly. So this is a flywheel. Okay, nice cylinder. I got lost in my word and I couldn't see what was wrong, and that's because I transposed my letters. There it is. Okay. It says that it gave us some information. It said that the flywheel had a mass of 40 kilograms. And they gave a diameter, which we're probably only going to want the radius. And they said that the diameter of the flywheel was 75 centimeters. Okay. And so then we can find our radius of the flywheel. So this would be what, 37.5 centimeters. So 0.375 meters, because we'll want everything in SI units no matter what. And then it says that it was initially rotating at 500 RPMs. Okay, so this will be our initial angular speed. And so instead of RPMs, we're going to write this as revolutions per minute, like this. And so what we need is we need this to be in SI units, right? So we have that one revolution is 2 pi in radians. And we know that in 1 minute, there are 60 seconds. So this is going to be a conversion that you're going to do like a lot. Like your kilometers per hour into meters per second, a lot. Okay, ad nauseum, as they would say. So it's 500 times 2 pi divided by 60. And so what do we get? And then this will be in, radians per second. You know, 52.4. There it is. Now I'm going to pick it to rotate in the positive direction. Plus 52.4 radians per second, like so. So I have my initial position and velocity. Now, this is the next thing, is that we're going to draw a representative diagram, okay? We do not want to draw an exact diagram. And the reason for this is that our next point was after 200 complete revolutions. We're not doing that. That's ridiculous. Okay. So what I'm going to do is I'm going to pick a new spot here. I'm going to say here was 200 revolutions from there. It absolutely is not, because 200 revolutions would be exactly right on top of it. And I'm not going around 200 times. So we're not going to do that. So let me go in and then I'll put our spot here. And we can see that this is that radius that I just calculated. We're still that same radius away here. That's great. And then I'm going to put in that this is going to be my new angular position here. Okay. And so what we have is that my angular position is 200 revolutions. And so I just need to convert this into radians. So let me do that. So we know that in 1 revolution, there are 2 pi radians. And then I can go in and, quote unquote, cancel out the revolutions. And so 200 times 2 pi, I guess we could write it as 400 pi if you wanted to, but let's probably write it as a decimal instead. So what do we get? Thank you, 1257. All right, and so this, we're going to move in the, I'll pick my coordinate system such that this is the 0. This way will be positive. Clockwise will be negative. We'll pick the standard coordinate system from math. Seems great. And so then this is going to be a plus 52.4. This will be a plus 1257 radians, like so. And then we don't happen to know how fast we're going at this point. We're still rotating the same way, like so. So we're going round and round. And what did it tell me? I think I know something else. Oh, the power was off for 30 seconds. Okay, so that means from here to here, this is our 30 seconds. Now, since we are slowing down, then what do we know about our acceleration relative to our velocities? Now, of course, these are angular velocities, and that's an angular acceleration, but the relationship's still going to be the same. How would we know that we are slowing down? Yeah, it's going to go opposite. So since I had it rotating counterclockwise for the rotations, then my angular acceleration is going to go clockwise, like this. Okay. And then, so this was during the 30 seconds when the power was off. And then they asked us another question, which was, how long would it take until it comes to a complete stop? Let me put the complete stop down here at this point. So we are still that same radius away. And so I don't know where we're at here. Maybe I'll put a little prime on that theta. But what we do know is that our angular speed or the angular velocity is going to be 0. Okay. And they wanted to know how long did it take to come to a complete stop. And it'll be the same alpha throughout the whole motion. So I could redo the alpha if we wanted to, but I guess I'm probably gonna, we'll see. We'll see. We got to find the alpha first. So then I have 1, 2, 3 kind of locations of interest. I have an angular position and an angular velocity here. I have an angular position and an unknown angular velocity there. I have an unknown angular position, but a known angular velocity here at each one of the locations. In between, we're supposed to have times, and in between, we're supposed to have angular acceleration. So, I mean, I could put, one more over here, but it's still the same as it was in the previous one, and so that'll be fine, I guess. So at the moment, I don't happen to know that. All right. So how's our diagram look? Seems kind of like how we did before. Only circles and, some, representative, right? Here, 200 rotations later there, a whole bunch more after that here. So the same kind of things that we did with straight lines. I try to keep the same colors for everything. The reds are accelerations, the blues are velocities, the greens and or blacks are either distances or positions. So purples I usually did for times. So if you look at chapter 2, it should be kind of the same color coding that I did previously. All right. So then we want this speed, we want this time, and this theta. So those are the things we're supposed to find. But in order to do that, we're going to need the alpha because alpha is in every single kinematic equation, right? The accelerations are in all of the equations, all 3 of the ones we use. And so then we're going to need to figure that out. And so if we're going to start here and end here, then I know the time, but I do not know this final angular speed at this point, but I know the angular position. And so then if we look at our kinematic equations, right, the one that doesn't contain the final angular speed is the second one, so we're going to use it to solve for alpha. Okay, so let's go in and do that. And so I'm going to start off with my theta is theta naught plus omega naught t plus 1/2 alpha times t squared. The final angular position is this plus 1257. The initial angular position was 0. My initial angular speed is plus 52.4. The time to go from here to here was the 30. Plus 1/2. Now the alpha, are we going to put in that we know the direction and write it in as a minus alpha for the direction and the magnitude and then solve for the magnitude? Or are we just going to write alpha like we used to and then find out that alpha is negative? Which would you prefer? Should I do a negative alpha or just the alpha? Okay, we'll do it like we used to. We'll just write, I don't know alpha, but then the time is 30 seconds squared. And so we want to solve for alpha. So to do that, I'm going to move this term to the other side. I'm going to flip the equation because you know I'm annoying like that. So we get 1/2 alpha times r 30 squared equals 1257 minus 52.4 times 30. And then we'll multiply by 2, divide by 30 squared. So then this cancels that. Divide both sides by the 30 squared. And this should give us alpha. So okay. Negative 0.7. Thank you. And the negative says I picked the wrong way when I picked my direction. And I'm like, but I didn't pick one. And so implicitly it was positive because there's no minus sign. So positive means I said it went counterclockwise. And so the negative means it goes the other way, which is clockwise. And so now we have our alpha. I could put it in the diagram if we wish. I'll go ahead and do that this time. Okay. And then now we can solve for this omega after the 30 seconds. And then we could answer other questions for the other part. Okay. So for the first part, they want to know what was this omega. So I'm going to use the first equation. So the omega is omega naught plus alpha times the time. So the initial omega was this plus 52.4. The alpha is negative 0.7. The time is the 30 seconds. And so we should get a positive how much? $50.3. And that'll be in, again, radians per second. So we went from 52.4 down to 50.3. So we have indeed slowed down. So that looks pretty reasonable. And then they want us to figure out how long did it take for the flywheel to come to a stop and through how many revolutions did it rotate. So those were the next two questions. Let's calculate this time. We know this final speed is the 0. We know the alpha through the whole motion. So let's use equation 1 again, but this time we'll find the time. So I have the final omega is the initial omega plus alpha times the time. And I put like a prime here and here. And if we load this, this is 0 equals plus 52.4. Alpha is negative 0.7. I'm solving for this time. So when I move this term to the other side, it'll become positive. So 0.7 times our time is this 52.4. Divide both sides by the 0.7. So then the t prime turns out to be all right. So this one is the 31.4. Ah, yeah, I got you. Okay, I'll fix it. There we go. All fixed. Great. 74.9. Definitely more than the 30. Looks pretty good. So that's the time. And then they wanted how many revolutions. So what we're going to do is we're going to find the angle, which will be in radians, and then we'll need to convert. Okay. To find the angle, we could use the second equation or the third equation. The second equation is already solved for theta, so I think I'm going to go with it. Okay. So let's do that. Well, let me do it this color, though. So do theta prime is theta naught plus omega naught t plus 1/2 alpha times t squared. And this would be the t prime. So the initial angle was at 0. The initial omega was our plus 52.4. The time to go from here all the way to the stop is the 74.9. And then this will be plus 1/2 negative 0.7, 74.9 quantity squared. So sorry, I have to do the two lines. So be careful with this minus sign right here. Don't lose that square right there. You know, the standard stuff. (1961). This was 1257, so being farther seems pretty good. But now this is again in radians, and technically they asked for in revolutions, and since there's a lesson to learn from this, hint, 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 then let's talk about how to get that. So then what we're going to do is we have that 1 revolution is 2 pi in radians. And so then what do we get for the answer in revolutions? So Manuel got 3,081. Everybody agree? Anybody disagree? Now Manuel got 312. The second one's right. Because what was the issue? What's the reason why I'm having us calculate this? The calculator thing. You need the 2 pi in parentheses. Otherwise, the calculator will do explicit order of operations. And I'll take the 1961, divide by 2, take that answer times pi. Because it'll read left to right. If you have a display, you'll see that it's not what you thought it should be, right? Divide by 2 pi divides by the 2, but then multiplies that answer by pi. So yeah. This is the reason I had us do this one. Because normally I don't care so much about converting back into non-SI units. I would have been just fine in radians. But I wanted to make sure that we checked out how to find those, revolutions. And that divide by 2 pi kind of thing. Super common mistake.